Hey everybody, this is Larry. This is me doing day 10 of the December Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord, let me know what you think about today's poem. And also, what was I going to say? Oh yeah, there are a couple of things. Uh, hmm, Forgot what I was going to say, so never mind. But I've been doing advent of code on Twitch, so definitely, if that's something, one is that I recommend it. It's kind of cute. It's some of the easier ones are similar to Leetcode, but definitely check that out. And yeah, that's pretty much it. I don't know what else to say about that one. But today's problem is Domino and Tromino tiling. I hope today's problem is a little bit more interesting because just I feel like in general in the past that has the last couple of weeks has been a little bit on the silly side, so we'll see. Okay, so already to be honest, catching from the name, I do have a sense of these. But well, let's see how it goes. So you have a 2-piece and a 3-piece, and okay. So I think the way to think about this is by recursion, right? And this is a thingy, a two row by n thing, and you have to return the mod. Okay, first thing I do, I know that I'm explaining it a little bit, but let's get the mod going because if you know, if you watch my stream or contests, whatever, I forget the mod a lot, so I try not to get a free penalty. And then here, I was gonna maybe draw it out, but the way that I would think about it is that there are really only two states, two possible states for something that has. How do I phrase this? I am doing this live, so it's a bit slow, fast forward, but that's why I'm thinking about how to explain this. But basically, let's say we have x filled columns. What are the possibilities, right? So let's say there are x filled columns, then you have something like let these be the dominoes. There are only two possible cases, right? So let's say x is equal to 3. You have this case and this case, and technically this case as well. But of course, that's it's very easy to see why there's a symmetry argument, right? Okay, so from that, it is actually enough to construct the answer, believe it or not, because now we can use recursion to figure out how it all fit together, right? So basically, we're trying to figure out the number of ways, and hopefully this ASCII art is good enough. I didn't really feel like putting up the Microsoft Paint just to do essentially the same thing. So, and I feel like this one, especially everything is square aligned, it hopefully makes sense. And okay, so basically now we can calculate, we can write out the two formulas in a way to kind of figure out how to answer it, right? So basically, let's say we have, how do we call it? Like, let's just say even. I say even because it's just like even vertically, but yeah. So get count for even. It's a very long name. You could use a better name probably, right? So let's say we have x, right? So what does that mean, right? Well, if x is equal to 0, then there's only one way of doing it. There's only one way to do an empty, one way to do an empty. Excuse me, hang on. That's the beauty of taping it live, and I don't want to edit it out because I don't know. So this is more authentic, if you ask me. I don't know. Let me know what you think. But anyway, so because there's one way to represent 0, right? That's the way that I would think about it. And then now we just kind of maybe think about how to add it up, right? So basically, let's say, so given, let's say, let's just for an example, x is equal to some random number 5, right? I use a random number to kind of help us visualize. So how many ways is there, right, to get, do x equal to 5? Well, recursively, let's think about only the let's think about all the possible cases, right? So there's one way. One way is just having another vertical domino. So this is x is equal to 4. So now we have get count for even of x minus 1. That seems reasonable, right? So this is basically vertical domino. I was gonna say a Tromino, but I guess domino makes more sense. Domino? I don't know. And then there's another way, which is, so another way to do it is you go to x2, you go to 3, and the logic here is that you have two horizontal ones, right? So if you have two horizontal ones, then now and that's one way to do it, and that fits it to x minus 2, right? Two horizontal ones, and of course this only works if you have at least two things, right? So okay, let's have actually total is equal to 0. I was gonna abstract it out, but and of course we did not forget about mod. No worries. I'm just kind of writing it out, right? So these are the ways to represent it by itself. Hopefully that makes sense so far. And then another way though is by using one of these LP, they're not really L's, but the 3 pieces, right? So what does this mean? Okay, so let's say, I'm going to erase this just for space. Hopefully those two cases make sense anyway. It's pretty straightforward. So that means that there are only the 2 ways, right? One is kind of going it here, like we said, and then the other one is going it here, right? And this is equals to x is equal to 3, right? Yeah. So basically going from 5, 4, 5, you're going to these things, and okay, maybe it's time to name the other function, right? Which is get count for, I'm going to say get sticking out, because why is it called sticking out? Because there's a thing sticking out, and you can use the symmetry argument to say that these are equivalent, because you know everything is the same, right? So yeah, so let's say x, and here we'll just return. We'll just pass for now, but we'll go back to it obviously. So here we can do the 2 ways to do L pieces. One is this thing. So yeah, and of course this requires x is greater than 2 as well, because if there's only, obviously if x is equal to 1 and you have this thing, you can't really take out an L piece, right? So these are the things that I think about. So if x is minus 2 is greater than 0, I know that I'm duplicating some code, but I'm just doing it for illustrative and teaching reasons. But yeah, but then now we can do total get count for sticking out. I just like this weird name. Let me, and then of course the other L piece, right? So you can all do it again. And of course, like I said, by symmetry reason, they're the same, but also, I mean, if you really don't believe it, and maybe some cases where maybe it feels more sketchy to do it, you can also, break this down to 2 different functions. It's not necessary in this case because I think, whatever, sticking out top maybe, and then another one for sticking out bottom, and then maybe you could prove to yourself that these are the same, right? But and then you would modify these functions. So these are things that I would consider doing, but in this case, I don't, it's not necessary, right? And then at the very end, return total. And of course, we do have a mod, I did not forget, but let's keep it, let's keep it without mods for now. Actually, I like to write it with mods inherent to it, but at least for now, I want to focus on the task at hand. Okay. So then now let's think about what does get count equals sticking out, right? So let's say we solved all this. It's okay. So let's say x is equal to 5. That means that it's sticking out looks like this or this or this. It doesn't really matter because they should be the same by symmetry argument. So then now we think about what are the possibilities, right? Well, what are the base cases, right? With x is equal to 0, that means that we're done. So we return 1. If x is equal to 1, oh wait, no, this is wrong. Sorry. If x is equal to 0, we actually return 0 because it means. And this is something that you have to think about. Maybe I rushed it a little bit. But this means sticking out means that you have with 0, that means that there are 0 full columns, and then you have 1 thing sticking out, right? And obviously, there's no way to do that, so there's 0, right? And then if there's 1, that means that you have 1 fold 1 and 1 thing sticking out. So that means that there's 1 because, well, you just remove it, right? Yeah. And then now going back to x is equal to 5 for the more general case, I mean, I just do that for visualization. So just template this out a little bit, not template, just so then here there really only 2. There's only one way, right? Is there? Well, no, but I'll get into it in a sec. So there are two ways to decompose this, right? One is the more obvious one where you just take the L piece. So you're going from here to so this is x equals to 4, right? So you have total, we add get count for even what's that, x minus 1, right? So that seems reasonable, right? I hope that makes sense. And then this, we get the answer from the count of that, and then we add that in. The other thing that you can do, so that's if you take an L piece. What happens if you take a how many ways is there to use a domino piece, right? A 2 piece. So a 2 piece, there there's only also one way to do it in a consistent recursive way, because let's say if you try to do like this piece, you would disconnect the graph, so it doesn't make sense, right? Or connect the board. So you can only do horizontal piece. So you do one piece, and if you do that, then you end up with this, and that is of course just x minus 1, right? Yeah, I think that's obvious. Maybe not, but see if you could. So yeah, and that's pretty much it, to be honest. And then the answer is, what is the question, right? What's the question? The question is number of ways to fully tile 2 by x n board. So that means get count for even of, what's it, n? N is the input. So that's pretty much it. We need to mod it, of course. I'm just gonna write it here just for a placeholder, but yeah, I mean we'll fix it in a sec, because okay, so it works for that case. That's great. Let's also put in some cases. I don't know if this times out. I mean, it'll be close to timeout. I don't know exactly. Oh, whoops. I said event instead of even. This might time out because I did a big number in there. We'll go over how to resolve the timeout, of course, but yeah, okay. I mean, that's not surprising. I just wanted to see whether maybe I did it in the wrong order. I just want to see, that we're correct for even a relatively big number. So that's 10, and 10 looks good. So that gives me some confidence, and enough confidence, because it should go through all these cases, right? And maybe even, I mean, once it gets bigger, it would time out for, obvious reasons, because we branch out multiple times. So yeah. So yeah, it works even for 15. So that'll be the beginning of us trying to optimize, because as you could see, and we'll try it again just for illustration, if you do something like 30, it's already times out, and n could be 1,000, right? So this definitely times out because we already saw it before. So yeah, there are a couple of things you can do. So, well, I mean, okay, now let's clean up the code a little bit and add the mod first. I just want to make sure that we're still kind of good. So before we resolve the time limit exceeded, we want to make sure our answer is still correct after refactorings, right? So one thing about refactoring is that you hope to have test cases, and you want to verify this correct, so that when you make those changes, your code is still correct first. So the first thing I would do is maybe combine these two, because now you can see that this is just this, right? That should look okay. So we made a small change. We run all the unit testing again, and then still looks good. And then the next thing we will do is we'll combine these two, also for maybe obvious reasons. And yeah, and this looks like all the things we have to do for now. Yeah, so that looks good. And then now we have to consider the mod, right? So we didn't actually get big enough for the mod to worry. So maybe we'll do the other one first, because we can't really test this in a good way. So one thing that I would say about testing is that you try to get a case for which it fails first. And right now it gets time limit exceeded if I try a big case, so you can't fail. Because if you can't fail, if you cannot get your test case to fail, then when like if for a test case it already not fails, and then you test it later and it still not fail, you prove nothing, right? So you have to get a test case for which it fails, so then when you make the changes to get it to be good, that you see that your code did something, right? So okay, so let's even though I guess technically this hides it away, so okay, so yeah, so the first thing I would do is dynamic programming or memorization or caching, depending how you want to say it. The key thing to notice is that for every same input into this function, you get the same output, right? It doesn't change. It will always be the same. There's no side effects. There's no weird class input or whatever, right? So that means that we can save the results because it's going to be the same for the same input every time, right? So, okay. So yeah, so let's write has cache. Let's call it is cache even. What are the possible inputs to this one, right? That's what we want to see. X can go from, let's see, 0 to n, maybe even n minus 1, but either way, 0 to n, which is of course n plus 1 items. So let's do that. So has cache, we will force times n plus 1, and then the actual cache even is equal to just, I don't know, it doesn't really matter because we don't access it unless the has cache even is equal to true, right? So then now we can do if has cache even of x is equal to true, then we return cache of even. One thing that I want to point out also is that the reason why we can do this is that we always go make this smaller, and as a result, we do have a DAG in our dependency, right? So there's no cycles, and that's why dynamic programming and memorization works. Maybe we'll go to a problem where that's not the case in the future, but anyway. But yeah, has cache even after we do all the calculation, we can do cache even of x is equal to total, and then just return cache even of x, right? Of course, we do the same thing for the sticking out. So let's get to it. Same idea here, right? What is the possible inputs to x? Well, x could go from 0 to n, roughly speaking, because technically this cannot be n because yeah, technically this cannot be equal to n because, well, that would be bigger than the input, but it's rough, it's good enough. As long as you're pessimistic in containing more items, and only a couple of items is fine, right? So yeah, so we do this here. We have the same thing here. So then we have if has cache sticking out of x, then return cache sticking out of x, right? And then of course once we're done, we save it. Should have used a shorter name maybe, but no worries, it's fine. I like to return this because in case that we do change anything, I don't know, maybe it's a force of habit. So let's run it real quick. Oh, did I use big N? Whoops. Let's make this big N. I feel like I'm used to having it as big N anyway. So this actually probably will give us the right answer even for big cases. So we verify for the existing things. Let's see if it will work for the bigger ones. Technically speaking, it might still actually time limit exceeded for the bigger ones for a reason that I'll talk about in a second, in a minute. But yeah, so this looks good, which makes me happy. But of course, we have this mod over here, right? So why did I say it might time out? Well, let's see if it times out. Because I actually suspect that it might. If not, then we're a little bit lucky. But it's still, we can improve on it. Even it'll probably be running very slowly, even if it doesn't time out. That's actually surprising. That's a little bit unfortunate. Maybe not. No, I mean, let me think about this. Maybe it's just fast enough. So the reason why this is suboptimal is because I mean, one is that if you're not using Python, you're going to get an overflow error in these things. So yeah. So one thing I would say is that if you're not using Python, you need to fix mod here, and you'll probably get wrong answer up to this point, and then you go fix it. But so the reason why I thought it would time out is because let's say we remove the mod, right? Because we only have mod in one place as far as I can tell. The thing is that you get a number that's very long, right? Look at how many digits this is. I don't know if you could see it on screen because the thing is like barking a little bit, but nonetheless, you get the point, right? This thing can be very long, and the reason why I thought it might time out, but maybe the inputs are not that intense, is because we're doing a lot of addition on a very long number, and that costs a lot of time, right? Yeah, that's the short answer, is that it costs a lot of time to mod these things. Oh, sorry, to add these things, because it just has a lot of digits, right? For example, this one has, I don't know how many digits, but let's say 1,000 binary digits, say, like 2 to 1,000, which is, I guess, like if you log that and then I don't know, right? Like, let's say like it has like 300 digits or something like that, right? I don't know. Well, that means that this is going to be like 30 times slower than, or some, I'm roughly speaking, and a lot of things are done in processor, the optimization, so it's not quite exactly that. But let's say it's like 30 times slower. Well, it's 30 times slower, right? And also, if n was even bigger, if n was say 10,000, this would get even bigger and would get like crazy big, right? So one thing that you can do, and it depends on your language actually and stuff like that, is just add mod here. You could the canonical way of doing it is actually do it after every operation, but you're only doing a couple of multiplying and because basically what is the domain of each operation is where I would think about it. For example, total is total is 0. Here, this number, we know that this caused the recursion, so this number is between 0 and mod. This one this one is also between 0 and mod. That means that total could be between 0 and 2 times mod. And here, again, because we have another 2 times this means that total at this point can only be 4 times mod at best. So when you do a mod, that only, that makes it, that invariant means that at worst, at every stages of the, at every stage, it is going to be at most 4 times mod. So if you use like a 64-bit int, like a long, that should be good enough, right? And that's why we don't have to, like, in theory, if you're not sure, or you have to do something funkier, you would mod it after every situation, or even mod it more intermediately, for example. But in this case, that is not necessary, or like for me, this is not necessary. Same logic here. As you can see, this has at most 2 times mod. So yeah, and because we know that this already returns a mod, we don't need to mod it here. So yeah, so just some tips and stuff, though apparently doesn't make out things that much faster, mostly probably because mod actually takes time to run as well. But yeah, since we look like we're good, we'll give it a submit. Apparently I have not done this problem on Leetcode, though I have done similar problems in the past. So yeah. Yeah, and with that submission, we have a streak of 619, and I forgot to do the analysis, but that's okay. I think at this point you probably know how to do it. Well, for every input, there are only O of n number of inputs, and for each input, it takes 4 operations or something. I mean, not 4 operations, but 3 additions and a multiplication, which something like that. So O of 1 operations, which means that in total, each input times O of 1 is equal to O of n time, right? And space also is very similar. Each input is O of 1 space. Oops. So each input times O of 1 space is equal to O of n space. And you can also obviously do the same here, and that's how you would break it down. Been talking a lot, sneezing a lot, and all this good stuff. But that's all I have for today, I think. Let me know what you think about this one. I think this one, this problem, or similar with problems to this one, are some of my favorite problems, to be honest, because I like combinatorics. It's interesting, and once you get the recursion, it's not that bad. So I don't know. Is it a medium? It's a little bit on a harder medium, because I feel like if you haven't had the right visualizations before, I think it's a little bit tricky to come up with. But once you have done a couple of these problems, I think it's easier to find the recursion, and it becomes easier, right? And of course, you can actually break this down to a bottoms up, of course. So you already know how to do what I have here. Use a bottoms up approach, and then once you realize that, you can also see that, you know, for every function you only look at negative -1 and -2. So you can actually further break this down to the ideal state of O of n time O of 1 space. See if you can get that. I have a video on dynamic programming progression, so check that out if you want to see how that's done. But that's all I have for this one. Like I said, I don't know. I dig these problems, but it is what it is. But yeah, for interviews, this is what I would consider maybe borderline. It's a little bit tricky. Maybe some people would give it as an interview question. I don't know if I would do it. It's a little bit too mathy. Or maybe not even mathy. Just like the idea of it is a little bit tricky. But yeah, but that's kind of my feedback. It is a little bit on a harder medium if you haven't seen it before. I would even go as far as saying that it's probably like, I would put it as a easy, difficult problem. But that said, I think some of the grading is because a lot of people have seen the similar problems. So there's some meta to it, which is kind of awkward if you ask me. But I would also say that once you have seen it, though, it is more straightforward. So maybe that's fair. I don't know. There's some balance somewhere. But yeah, that's all I have for this one. Let me know what you think. Hit the like button, hit the subscribe button, especially if you want to give me some love and support. Would appreciate it. And I'll see you later. Join me on Discord, chat about this problem, chat about another problem, do whatever you want to do. And yeah, I'll see you later. Bye-bye.